Okay, in today's lesson we are going to learn about how to write the slope of a tangent line to a given function f of x at a specific point x. So there are two formulas that we want to review. The first is point slope form, which is y minus y1 equals m times quantity x minus x1. And remember that x1, y1 is any point on the original graph f of x. The second is slope-intercept form, y equals mx plus b, where m is the slope and b is the y-intercept. Now, when we write the equation of a tangent line to a given x value of a function, there are three things that we need to do. First of all, for f of x, we want to find the point xy, and we can write this point as x comma f of x. Once we have the function and we know which point we're working with, then we want to find the slope of this function at that x value. And we can figure this out two ways. One, if we have a graph and is linear, we can get the slope just from looking at the graph. The other way is like we learned yesterday, where we use the equation of f prime of x and we can plug the x value in. Lastly, once we have the point from the original function and the slope from the derivative function, now we plug this point and that slope into point slope form. Now, before we can go ahead and talk about how to write these equations, we want to first go ahead and address the scenario when the derivative does not exist. There are three situations that we want to be aware of. The first is when the function is discontinuous. And we talked about this last chapter. We talked about the three different types of discontinuity, and we talked about how there was jump, point, and infinite discontinuity. And in any one of those three scenarios, the derivative does not exist. Another time when the derivative doesn't exist is when there is a corner on the graph. And a corner is most easily described by looking at this graph I have right here. Each of these three areas that I circled, that is where pieces of the original function connect. And you'll notice when you look at that connection, it's kind of like the graph is just going along its way and then bam, switches like that. When that happens, that's what we call a corner. And if we were to find the slope of the graph from the left and the slope of the graph from the right as we were approaching that x value, they would not have the same slopes. Therefore, since the limit from the left and the limit from the right would not be approaching the same slope, then the derivative would not exist. And you'll get into this more in calculus next year. For right now, you just want to be able to recognize on a graph where we happen to see those corners. The last time when a derivative doesn't exist is if there is a vertical tangent line, and that would be like what we see here in the drawing I drew number 3. Again, we're not going to see a whole lot of that this year. The two scenarios that we expect you to really recognize are these first two here. We talked last chapter about discontinuity, and we should be able to look at a graph and recognize where we see corners. Okay, so now we know when a derivative doesn't exist. Let's talk about how we write the equation of the tangent line when the derivative does exist. All right, now in this first example, we are giving you the original function f of x, which you see right here, and we are giving you the derivative function 2x minus 3. Right now, we don't know how to easily get the derivative function. We learned yesterday how to do limit definition, and it was quite cumbersome. Once you learn how to do the shortcut method, we'll no longer give you the derivative. But for right now, we're just going to give it to you. So we want you to find a few things. Number one, we want you to find f prime of x, and we want you to write the equation of the tangent line to f of x at x equals 1. All right, so first of all, we need to get a point using the original function. So since the x question that I'm working with is x equals 1, I'm going to plug 1 into f of x. And I will get 1 squared minus 3 times 1 plus 1, and that is going to give me negative 1. So that means the point that I'm looking at is 1, negative 1. And that is the first thing that I need. The second thing that I need is the slope of f of x at x equals 1. And the slope of f of x is going to be written with symbols as f prime of 1. What that tells me is the slope of the function f of x at the x value of 1. And to find that, I just plug 1 into my derivative equation. So I'll have 2 times 1 minus 3, which ironically also gives me negative 1. That's a coincidence that does not always happen. So now I have a point and I have a slope. And then lastly, I'm going to go ahead and I'm going to write my equation using slope-intercept form. I'm sorry, point-slope form. So I will do y minus y1 equals m, x minus x1, and for the y1 and the x1, I use the values from my point. So y minus negative or y plus 1, and for my slope, I use the value I see here, negative 1, x minus 1. And then we can leave our answer just like this. Similarly to how we talked about how we don't have to simplify radicals in the denominator and whatnot, same thing is true with our equations of our lines. We can absolutely leave them in point-slope form. Okay, in this next problem that we see here, we are given h of x and the derivative, h prime of x. Again, we're not expecting you to know how to find the derivative right now. We are giving it to you. And in this case, we also want to find the equation of the tangent line to f of x at x equals 1. Unfortunately, part of the problem got cut off. So let's just write it in so that we have it. So we want to find the equation of the tangent line. So equation of the tangent line at x equals 1. Okay, so we've got our 3 steps. First, we have to go ahead and we have to find the point. So step 1 is I need the point x, y. And to get the point, I plug that in my original function. So I'm going to do h of 1 to ln of 1, and we should all know that ln of 1 equals 0. So we have 2 times 0, which is 0, giving me an ordered pair of 1, 0. All right, next I need a slope. And to get our slope, we use our derivative equation. So we do h prime of 1, which is 2 divided by 1, or 2. So my slope is 2. And then now, lastly, I put these together. Y minus y1 equals slope, x minus x1. And in this case, we can just go ahead and write it as y equals 2 quantity x minus 1. If you want to distribute, you can also write it as 2x minus 2, but not necessary. All 3 of these answers would be acceptable. All right, let's go ahead and take a look at how we do the same procedure when looking at a graph. Okay, in example 3, we have a graph here. And first of all, before we even get into the problem, let's talk about where our derivative would not exist. Let's first take a look at where we see any discontinuities or corners. And looking at this graph, I can see corner, 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 corner. Last chapter, when we talked about limits, we talked about how those values would still be continuous, and that's great that they're continuous. However, the derivative would not exist there because of the way that those 2 segments are connected. Okay, so let's take a look at our questions starting at the beginning. So first of all, we have, we want to estimate the value of g prime of negative 6. Now remember, when we see this g prime, what that is saying is, what is the slope of g of x at x equals negative 6? So if we look at our graph, when x is negative 6, at that point, that's part of a linear segment of my line, right here. And when my graph is linear, we know that the derivative of a linear function is just equal to the slope of that function. So if we just figure out our slope here, I'm going down 3 over 2, then any point, doesn't matter where I were to pick it, any point on this line segment here is going to have a slope of negative 6. So this here would be equal to slope of negative 3/2. The same slope that we see when x is negative 6. All right, we want to estimate the value of g prime of 1. So again, we're trying to figure out, when I'm over here at x equals 1, what is approximately the derivative there? What is the slope there? And again, since this line segment is linear, we can go ahead and just do rise over run for the whole line segment, up 2 over 3, and that would be the slope for any point on this line I have just colored red. All right, now if we look at g prime of 7, over here at 7, that is part of a horizontal line segment, and we know that horizontal lines have a slope of 0. So notice how there was no equation necessary. We were able to figure all of this out just by looking at the graph. Now when we get to part D, we want to write the equation of the tangent line at x equals -6. Now when we're writing the equation of the tangent line, remember we need three things. We need a point, we need a slope, and then we put it together into point-slope form. Now when you're coming up with a point, we don't want to estimate. Like right now when I look at this and I look at when x is -6, I think it's 2.5, I'm not quite sure. When you're writing the equation of a line, you can pick any point that is on this line. So what I could do here is I would just pick one of these endpoints, any one of the points on this purple line segment, and I could use them. So I would either use -7.4 or -5.1. Now, technically, if you used -6, 2.5, and that was a valid point, then that would be okay. However, that's a gamble because it doesn't always look exactly like what you see on the graph. Now, we already said the slope at x equals -6 was -3/2, and then now we just pick one point or the other and go with point-slope form. So let's just say I use this first point, then I would have y minus 4 equals -3/2 x plus 7. And if you would have used the other point, your answer would have been y minus 1 equals -3/2 x plus 5. Now you might be like, well, hold on, how come I have two answers? Well, when you're working with point-slope form, which is what I wrote right here, there are going to be multiple answers. However, if you were to simplify them and solve for y, then they would all have the same slope-intercept form. That's what this SI stands for. Okay, pause the video and answer parts E and F. Okay, so for part E, hopefully you picked the points -1, or 2, 3, so that we didn't have to estimate exactly where that point would be. Again, you probably could have figured it out, but why should you work so hard to figure out what the y-coordinate is when you can use any point on that red line segment? For part F, since when x is equal to 7, this is part of a horizontal line with a slope of 0. Horizontal lines are always of the form y equals a number, and that's why our answer here is y equals 3. All right, for part G, the question asks, over the interval -7 to 6, list the x-coordinates where the function has a horizontal tangent. When we're looking for a horizontal tangent, what we want to look at is anywhere that we see a max or a min on our graph where it is defined. And if we look at our graph, we're going to see right here, when x equals -3, I would have a horizontal tangent. And when x equals 4, I would have a horizontal tangent. So the way that you tell if you have a horizontal tangent, what you want to look for is you want to look for where you see a max or a min of a curve. And this occurs at x equals -3 and x equals 4. And then we talked about what the slope of the graph is at, -5, -1, 6, and 2. And like we mentioned at the beginning, those are all the points where our graph is discontinuous. So right here, the derivative does not exist because these x values are corners. So since the derivative doesn't exist, the slope doesn't exist. So these points have no specific slope because the derivative doesn't exist. So you can either say no slope, you can say D and E, either one of those would work there. And this is going to occur if we have a discontinuity or a corner in the graph. All right, that is it. Homework is worksheet 2.